let me give a couple motivations for what we're doing. So why can we be interested in counting square-tiled surfaces? So the first motivation is called meanders. So initially it comes from some applied problem in physics or chemistry, I guess, about enumeration of polymer chain foldings. And mathematical formulation is the following. So meander is a pair of simple closed curves on a sphere up to homotopy. So simple means non-self-intersecting, well, maybe I should say that a transversal pair. So we're counting pairs of curves up to homotopy, and those curves, they intersect each other transversally on a sphere. So because it's up to homotopy, we can move one of our curves to be an equator of the sphere. And let's unwrap it into the plane. So something like this. So let me just draw something that is a meander. So maybe something like this. And now let me draw something a little more systematic way. Okay, so maybe something like this. Well, the question that people are interested in is understanding the asymptotics of these things, maybe in different regimes. For example, one regime you can choose is you can say, okay, look, there are these arcs, small arcs, sort of minimal arcs. The authors call them pimples. So let's fix those pimples, and let's say that we are sending the number of intersections. So in this case, it's 1, 2, 3, 4, 5, 6, 7, 8. So the n equal 8. So we're sending this n to infinity, and we want to understand how many configurations of these pairs of transversal curves do we have, given that the number of pimples does not change. So number of minimal arcs does not change. And so here is why square-tiled surfaces are useful here. So let me actually replace each crossing with a square. So I'm kind of drawing a dual graph to this configuration. And then the vertical sides of the squares attach due to the horizontal side. So they just follow the horizontal side. And one of the curves of the meander here intersects our square, and then it follows to this square. So we're going to identify this edge, let's call it A, to this edge. And then this edge B will be identified to this edge B. So remember that we're identifying by rotation, by pi rotation, because we're identifying two top sides. And then this C will be identified to this, and so on. So this D is to this. And then we identify the vertical sides by parallel translation, as usual. And then we go on and on and on. So we are folding sort of all of the sides of our square-tiled surface. We're getting closed surface. and it's a surface of genus 0. So let's see what is the role. Which role do the pimples play? So pimples means that we identify two adjacent sides. So let's say the picture locally looks like this, and so that means that we're getting exactly angle pi. So there are 4 pimples. That means that we are in a stratum of square-tiled surfaces of genus 0, and in this case equal to 8 is the number of crossings, which became the number of squares. And then because we have 4 pimples, we have 4 minus 1s, points where the axis angle is pi. And then we have something, and we don't know what. But remember that the asymptotics of anything that could be here is dominated by the one where we have where we have all ones. So 1, 1, 1, 1, 1. So this means we are actually looking for the answer for the problem that we just formulated here. I should say that it's not exactly the question we're looking for here, because this set is actually much larger. So we are restricting to a certain subset. For example, the vertical sides of the squares always follow this horizontal equator line. So that means that our squared-out surface sort of unfolds into one strip in a horizontal direction. But also, in fact, if you start with one square and start moving vertically, that means you are following the second curve of the meander, and you're always following it. So if you follow vertically, it also unfolds into a vertical strip. So that means we have our squared-out surface in the horizontal direction has only one strip, and vertical direction has only one strip. So we are working in a small subset here, but nevertheless, this problem has an answer, and it uses this number as well. So this is it's really a useful way to think about meanders, even though we're not looking at the whole number, we're looking at the part of it. This number will be used in the calculation as well. Yeah, and so just to finish with the meanders, you can go further and you can ask like a natural generalization of this question. So the natural generalization of this question would be, what is the asymptotics of the number of filling pairs of transversal multicurves on genus G surface as the number of crossing grows. So what do I mean by that? So suppose we are working on genus 2 surface. Here is one multicurve. So multicurve is just a disjoint union of simple closed curves on a surface. So here's one simple closed curve, no self-intersections. Here is another. They do not intersect, so they form a single multicurve that has 2 components. And here is a second multicurve. I'm going to go around this hole and I'm going around this hole, and then I don't know, maybe I can throw in this curve, and so these 3 green curves will form a second multicurve. And filling means that the complement to the union of these 2 multicurves is a disjoint union of topologically disks. Yes. So that's filling. I explained filling, I explained multicurves. Transversal means that they intersect transversally. I explained that. So, and they live on a genus 2 surface, and the number of crossings is the obvious thing. And then you can ask how many configurations up to, for example, homeomorphism of a surface are there. And so reformulating this question into square-tiled surfaces language in the same way we would obtain this picture. You can persuade yourself that this picture transforms into this square-tiled surface as we do the substitution by squares. And so the green curves here are these three vertical curves. Sorry, I should say about identifications. As usual, it's the surface that we've already seen many times. And the red guys are the horizontal ones. So yeah, this square-tiled surface is also nice because you see immediately that pair of transversal multicurves. You just take horizontal curve for each strip and draw it in red. So there is one for here and there is one here. And you see I'm not taking two because those would be like homotopically the same. If I slide the red curve down a little bit, it doesn't change the homotopy class. But if I sort of cross this place where there is a conical singularity, so once I hit the conical singularity, something's going to change. So here is another curve, and the same thing with the green curves. Okay, so this is another type of questions that square-tiled surfaces could help answering. Okay, so let me now go to the second motivation. So second motivation has to do with the volumes of moduli spaces, which also called Mazurovich volumes. I'm gonna talk about a particular example of such volumes. If we consider moduli space of algebraic curves of genus G with n-marked points, then the cotangent bundle of that space can be identified with the space, moduli space of quadratic differentials, meromorphic quadratic differentials. So what do I mean by that? So I think of it as a pair. X is algebraic curve of genus G with n-marked points, so it's a point of the space. And Q is a meromorphic quadratic differential on X with at most simple poles at marked points. So what is a quadratic differential? Meromorphic quadratic differential. It's if you look locally in some neighborhood, it looks like some holomorphic function times dz squared. So you can always choose a complex coordinate or a chart on your algebraic curve so that it will be dz times some meromorphic function. And in this case, everywhere except marked points, it's a holomorphic function. But at marked points, it's allowed to be 1 over z times dz squared. Okay, so this space of quadratic differentials, it's a cotangent bundle, and cotangent bundle has a natural symplectic form. So we can ask, what is the volume of this cotangent space, cotangent bundle with respect to this symplectic form? And the fact is that that number is equal to STGN minus 1 to the n, 1 to the 4g minus 4 plus n. And so let me give you a hint. What is why quadratic differential appears here, and what is the relation between these two seemingly different problems? So the relation is that if we look, let's look at my favorite square-tiled surface. And let's remember that we put this picture on a flat piece of paper. So a flat piece of paper can be identified with C. So this way, if we embed our picture in C, every point inside a square gets a complex chart. And in fact, every point on an edge also gets a complex chart, except there is a transition function here. And the transition function is like Z goes to Z plus some complex number C. So it is a holomorphic transition function. So we get a global complex structure, and that means that we're working with algebraic curve here. Algebraic curve of genus G, of genus 2. But flat piece of paper not only comes with the complex structure, but it also comes with a holomorphic one form, dz, or let's say a quadratic differential, which is dz squared. This differential dz or dz squared survives under these transition functions. So d of z plus c is equal to dz. If we do rotation by pi, then that means we're applying z goes to minus z, let's say, in some chart. So if we identify two sides by rotation, like this, then we get this transformation, and the dz doesn't survive it. So d of minus z is equal to minus dz, but the quadratic differential, so squared thing, does survive. So that means that the quadratic differential dz squared and the complex structure descend to give this object. And so that means that square-tiled surfaces are points of this space. And it turns out that because we compose them from unit squares, they serve the role of integer points in the space. And one of the ways to compute volumes is to compute integer points. So this is the relation to volume. Okay, so maybe now let's go to the result. What is the answer, or how can we obtain this number? The volume of QGN or the STGN, and so what is the answer? So we need to prepare a little bit, and I need to give some definitions. So let me call it maybe main theorem. So first, let me define Kontsevich polynomial. So Kontsevich polynomial will be denoted NGN, and it's the following thing. So it's a homogeneous symmetric polynomial that has n variables. And so we define it as a sum over all partitions of number 3g minus 3 plus n. And all monomials, all variables have even powers. And there is this symmetrizing coefficient here. And the coefficient of such monomial is the following number. So it's an integral over the compactified MGN of psi1 to d1, psi n to the dn. So this is called the intersection of psi classes. And the only thing we need from this coefficient is that it can be computed recursively. So we can get hands on all of these coefficients for pretty large G and N polynomials. And of course, we have hope to use, if we can express our answer using these numbers, we have a hope to use recursion for these numbers in order to have recursion for volumes. So the second thing is I will want to decorate certain graphs. So let me say graph decoration. So let me start with any graph. So maybe, so let me make vertices red. And let me make the edges blue. So I started with a graph. It can have loops. It can also have something called legs. So legs are sort of these half edges that are hanging but do not end in a vertex. And I will also have my vertices labeled by some integer numbers. So let's call those numbers G1, G2, G3, and G4. So I start with the graph with legs. Okay, so let's call graph gamma, and the set of vertices of this graph will be always denoted V of gamma, the set of edges E of gamma, and there will also be legs. And now I want to decorate this labeled graph. So what I'm gonna do is on each edge, I'm gonna put a variable, W1, W2, W3, W4, and the legs will get zeros. So edges decorate with variables, Wi, and legs decorate with zeros. And vertices, we will decorate vertices with Kontsevich polynomials, N, Gi, Ni, where Ni is the valency of the vertex. So for example, so let's look at this vertex, and it will be decorated by a Kontsevich polynomial N, G4, comma, there are three, the valency is 3, there are 3 half edges going out of this vertex, so 3. And then, so it should depend on 3 variables. And what are the variables is the variables that are written on half edges. So it's W2, W3, and W3. So what will be the, okay, so let's do this one. So here we have the G3. There is only a 1 half edge, so the valency is 1. And the only variable we have here is W4. Okay, and so let's do this one maybe. So the first index is G1. There are 3 valency, the valency is 3, so it's 3. And so there is a space for 3 variables. One is W1, and another is 0, and another is 0. Okay, so this would be called graph decoration, and once I have a decorated graph, I have a polynomial associated to this graph. To decorated graph. Let me call this polynomial P gamma. And the polynomial depends on the variables Wi through W number of edges. And so first we just take the product of all the variables. And then we further multiply it by the product over all vertices of the graph, where for each vertex we take the corresponding Kontsevich polynomial that we see on the decoration. So maybe this should be in red, and this should be in blue. Okay, and then the last thing I'm going to perform with this polynomial is I'm going to replace each Wi to the power, say, mi, with the following number, mi factorial times zeta of mi plus 1. So these numbers have explicit expressions. So this is a known number, and you know, if I'm taking products of these powers of wi's, I'm taking products of this, and then I extend by linearity. And so once I perform this operation, so let me maybe call this operation Z. So I'm going to say that the volume of the graph, is this operation applied to this decorated polynomial corresponding to this graph gamma. Okay, and so now we're ready to formulate the theorem. So the theorem of Delacroix, Goujart, Zograff, and Zorich. The number we're looking for, the volume of QGN, or the number of square-tiled surfaces in the principal stratum, is equal to some constant that depends only on G and N, and it has explicit expression, times the sum over all stable graphs of genus G and with N legs, times some constant that depends on the graph, times the volume that we just defined. Okay, so let me maybe write down those constants so you know that they're not scary. So this one would be 2 to the 6g minus 5 plus 2n divided by 6g minus 7 plus 2n factorial, something like that. And the second constant is 2 to the 1 minus the number of vertices divided by the order of by the number of automorphisms of the graph. Okay, so I still need to explain what is this object, and I'm going to do it on example in a second. But roughly this formula says that to each such object called stable graph, we have associated number that can be algorithmically computed like this. And then we just take the sum all of them with certain coefficients. And this is the answer. And it's pretty straightforward to program this to get numbers for certain explicit values of G and N. So that's the usefulness. So let me use 2 minutes to explain what is stable graphs. So stable graphs, they parameterize points on parameterize boundaries of the moduli space of algebraicos MGN. And so let me demonstrate how to generate all stable graphs. My favorite way of generating stable graphs. So let's start with a genus 2 surface. Can you see here? Yeah. And I'm going to start listing all multi-curves I can have on this surface. And I'm going to start with just one curve, multi-curve consisting of a single curve. So there are, in fact, up to homeomorphism, there are only 2 such curves. So any curve you can draw, you can find a homeomorphism which sends a picture to this or this. So this curve is called separating because if we cut along it, we get 2 tori with boundary. And this one is called non-separating. If we cut it, we get a genus one single component, genus 1 surface with boundary. And then I'm gonna keep adding multi-curves to each of these pictures. So to this picture, I can add another non-separating curve. And in fact, I can come here from this as well. So if I add to this picture a separating curve, I get this. And well, there is nothing else I can do here. With this one, I can add another non-separating curve, and I'll get picture like this. You know that you are done when you have enough multi-curves. And enough multi-curves means that if you cut along them, there is no more to add, because topologically, you're going to have a union of spheres with 3 boundary components. Okay, so now from this picture, we're gonna go and we're gonna go to the boundary of the modular space. What does it mean to go to the boundary of the modular space? It means start contracting those curves. And so if I can do this in parallel, so from this picture, if I contract this curve, I obtain this picture. From this one, I obtain this one, and then further on. So I pinch those curves, I obtain singular surfaces. Well, it's not very convenient to draw such pictures all the time, so we will consider dual graphs. And the dual graphs is I just take and replace each subsurface with a vertex, and then I connect those subsurfaces with an edge if they touch at a point. So, for example, these two tori get replaced by these two vertices, and then since they touch at this point, at this red point, they're connected by a red edge, and I will write 2 ones on each of the vertices to remember that those were genus 1 components. Similarly here, I have only one component, but it self-intersects. So I'm going to draw a loop, and I'm going to remember that the surface is genus 1, in fact. Genus 1 with 2 points glued, and so on. And so this is for genus 2 and n equals 0. These are all the stable graphs that we can find. And then we can perform the decorating and finding the polynomial and so on. Okay, so in the 5 last minutes, what I want to do is well, I wanna say a couple of words why this result is true. So let me take a new piece of paper. We started with Kontsevich polynomial, and I need to say why. What is the relation of Kontsevich polynomial to this story? And this has to do with the theorem of Kontsevich, and it says the following things. So let me define ribbon graph. So ribbon graph, one can think about them as graphs embedded into surfaces. So precisely, ribbon graph is a graph with a cyclic ordering of the edges. So if the edges are ordered, then we can do something like this. So we can draw a little ribbon around each edge, right? Each open edge. So thicken it a little bit and lay it out flat on a paper locally. But then because we have an ordering prescribed around each edges, we know how to connect those ribbons. So we actually get in a ribbon structure all over. And so this one will be genus 0, and it has 3 boundary components, the 2 small boundary components and 1 big. And then I want to count, so what is the number of the ribbon graphs of genus G and N boundary components with integral length edges such that the lengths of the boundaries are W1 through Wn. So once I prescribe lengths to the edges, so for example, let's say that this edge gets length L1, this edge gets length L2, and this edge gets length L3, the boundaries also acquire edges, because each boundary, for example, this big boundary composed of going around L1 and then going along L2, along L3, and then again L2. So W2 is L1 plus 2L2 plus L3. And so I'm fixing these numbers, but I let these numbers vary. And so here's the theorem by Kontsevich. This RGN as a function of the number or the cardinality of this set as a function of W1, Wn is a polynomial. Of degree 3g minus 3, 6g minus 6 plus 2n. And the second part is that the top degree part of this polynomial is Kontsevich polynomial, is NGN of W1, Wn. And so if we were to count asymptotics of the square-tiled surfaces and we found a ribbon graph somewhere, it's plausible that we won't need the whole polynomial, but we would only need the top degree part. So that's why we only remember this in our formula. And so let me locate the ribbon graphs for you on a square tiled surface, so it doesn't look completely unrelated to what we were discussing before. So let's go back to this picture. So we said that there are these horizontal curves, and that if we slide that horizontal curve, it sort of fill out this rectangle. And if we do the same with this horizontal closed curve, which is in fact a multi-curve, and remember, each time we see a multi-curve, we can think about a stable graph. So that's how stable graphs come into play. And then this curve swipes out this rectangle. So what's left of this? Only the horizontal edges here that connect the singularities are left. So once we throw out this red part, we're left out with this graph. And because this graph naturally sits in a genus 2 surface, it has a ribbon structure because it comes from the surface, so we can thicken it a little bit, and it has the ordering of the edges. So this is a ribbon graph. This is how ribbon graphs appear. So if we wanted to reconstruct this surface, we would have to remember, well, the combinatorial decomposition of it. But then once we have ribbon graphs with certain boundary components, we have to paste in those red parts. And those red parts also have some parameters like width and height and maybe the twist. And so we start with this skeleton, which is a ribbon graph, and then we glue in the body, which are the cylinders. And if we accurately count all the parameters, then this is the procedure that we obtain. So that's the whole idea of the formula. Okay, so I'll stop here.